Okay, well, good afternoon. For those of you that haven't joined us before, my name is Mark Stewart and I'm the Director of RSK Geosciences business, and I'd like to welcome you all to the latest in our Down to Earth webinar, which today is being given by Siôn Roberts, who is going to give us a presentation on some of the geotechnical challenges of developing former coal mining sites. First, I'd like to briefly go through our housekeeping with you. So all attendees' microphones are automatically muted throughout the webinar, so you can hear us, but we can't hear you. During the presentation, you can post questions and using the box to your right, and then we will have a Q&A session at the end. We'll answer as many as we can. If we can't answer any of your questions, then we'll try and get back to you after the webinar. Shortly after the webinar, you'll receive a short survey. If you could take a few minutes just to provide us with some feedback, please, so we can improve our future webinars, that'd be most appreciated. So without further ado, I'd like to introduce to you Siôn Roberts, who's going to be presenting to us this afternoon. Siôn has been with RSK since 2007. He's one of the principal consultants based in the Geosciences Helsby office in the Northwest. He's our technical lead for the mining support group, who provides support to colleagues around the country and clients working on coalfield sites. So over to Siôn.
Great, thank you, Mark. Thanks for the introduction. Hello, everybody, and thank you for taking time out of your day to attend this webinar. I'm going to turn my camera off and we'll get stuck in. So the presentation today, the webinar, is well attended. So thank you for taking the time. And it includes people from local planning authorities, consultants, designers, contractors and academics. You will all have your own particular interests, specialisms and perspectives. And this talk aims to give a high-level overview based on my practical perspective in assessing coal legacy issues at RSK and bringing former sites to development. The talk will comprise three broad themes: coal mining legacy, challenges posed by some of these legacies, and in particular ground movement, touching on data collection, modelling, and using surcharging as an approach to ground treatment. The talk will then conclude with closing remarks, which should take half an hour or so. I wanted to include this photograph on the right as an introductory slide. It was taken at the former UK coal surface mining sites in the northwest of England, which is now part of the Logistics North development site. In fact, this particular photo is now overlain by Country Park. And it illustrates well the ground conditions that can be present, in which we may not necessarily be able to observe through the prism of a borehole or trial pit. And we will return to this slide later on in the talk. So, coal mining legacy. Coal was formed over a long period of time, principally within the Carboniferous period. And it's fair to say that we would not have a great deal to talk about if the UK was not positioned just south of the equator 360 million years ago. The deltaic landforms, climate and ground movements formed ideal conditions for the cyclical inputs of mudstones, silt, sands, and the accumulation of peat and subsequent development of coal. Coal has a long history of extraction in the UK, which peaked during the late 19th century with up to 1,500 collieries present in the UK at the time of nationalisation in 1947. The Coal Authority is the statutory consultee for development on the coalfield, and about 15% of the coalfield, shown here in black, is classified as being development high risk. This is defined as where recorded coal mining risks are present at the surface or shallow depth and are likely to affect new development. It's also worth pointing out that there are an estimated 150,000 recorded coal mine entries in the UK. However, the actual number of mine entries is likely to be much higher on account of not all of them being recorded. So moving on to methods of extraction of coal. Coal was initially extracted by surface exposures and progressed to underground methods. On the left here is the former Chatterley Whitfield colliery in Stoke, and on the right is an example of a mine abandonment plan shown where coal has been extracted in red shading. Up until the Coal Mines Regulation Act 1872, not all abandoned mine workings were required by law to be surveyed and recorded. Here we have two examples of worked coal seams, clearly showing the voided nature where coal has been extracted, which is termed the extraction thickness. It is interesting to note that the image on the right shows part of the coal left in situ to support the coal roof. I should acknowledge that these two images are taken from the internet and show workings from what I believe to be the Rams coal seam at the former Caretaker surface coal site, which was subsequently removed in part by UK Coal. And we can see here on the image on the left is the Rams coal seam as exposed by UK Coal, and we can appreciate, or begin to appreciate, the panels of coal that have been removed and the resulting pillars to support the overlying roof. The image from the left is again taken from the internet, whilst the image on the right is taken from Charleston Colliery by Neil Hutchinson at RSK. Surface coal mining, also referred to as open cast mining, was undertaken at the former Orgreave Colliery over in Rotherham. It was subsequently open cast up to 100 metres deep, a kilometre in width and 3 kilometres in length. The image on the right is an old open cast void from the 1950s. It's an abandonment plan, and again showing, similar to the previous slide, prior removal of coal by underground mining, which was subsequently exposed during open cast methods. This is the last side for open cast coal legacy, clearly showing a significant void of 30 to 40 metres on the left. The slide on the right shows bulk excavation of overburden to expose the steeply dipping Pemberton and white and black coal seams. It's worth mentioning on the top right-hand corner of the slide, you can see the removal of the Caretaker colliery tip, which is underlain by the glacial deposits, and on top of the coal strata where we access the coal reserves. Nearly there. Here we have some images of some mine shafts, mine entries. Top left is in Donington and shows a relatively high density of mine shafts. The one on the shaft on the right is clearly voided in the image that we can see there, whereas the shafts and the two lower images are filled. The one on the right being excavated down onto competent founding strata for the remedial capping slab. So we have briefly covered why coal is present, and how it can be accessed and removed from the ground, or some examples at any rate. Historic coal mining, and ignoring the current coaling operations that are ongoing in the UK, albeit diminished, has left landowners and developers with a legacy, one which represents opportunities, but also presents challenges to their consultants and design teams. I've included here an aerial image of a former Caretaker surface mine, which had a long history of deep mining and surface mining, both historic and recent. This would be a long and interesting rabbit hole for me to disappear down, but suffice to say, investigation, assessment and treatment during and post-coaling has resulted in the delivery by Harbour Crew of the largest regional logistics and manufacturing schemes in the Northwest. So, what next? There are various challenges that the legacy of coal mining in the UK is left behind, and one key aspect is ground movement. There are various mechanisms, ground movement, be that the consolidation of open cast backfill, heave of materials, ground movement induced by mine shaft collapse, or void migration from shallow workings. There are various mechanisms which can induce ground movement, such as collapse compression, inundation settlement, from rising groundwater or surface water infiltration, self-weight settlement, changes in ground level as part of development earthworks, and building or construction load induced settlement. There are other potential challenges, including mine gases, contamination, and aggressive ground conditions, but we won't be focusing on those in this presentation. So, in terms of ground movement, the key aspect really is, in this talk, is for the collection of data for ground movement. And in terms of assessing ground movement, it is a key to design an appropriate ground investigation based on the ground model created from all available sources of information that we can review before going to site, be they abandonment plans, geological plans, archives, archive information, existing reports, etc. If we are to assess ground movement, advising our clients and the design teams on the ground constraints that need to be taken into consideration, we need to collect data that characterises the settlement behaviour of the different ground conditions present across a site. This is one approach, and we hope to illustrate in the following slides. So we need to start with a ground model. Here we have a cross-section taken through a site which shows an area of old 1950s open cast backfill on the right of the image, more recent open cast backfill on the left-hand side of the image, historic surcharge mounds, and ground treatment mounds here. The eagle-eyed among you may wonder why the coal seam doesn't continue to link up to open cast excavations. And this was the coal washout channel was present here. So in effect, there was no coal present. So high wall areas were okay. So we start with a ground model, and then we need to collect data on ground movement. A variety of techniques that we've used over the years. This here is an image of a vibrating wire plate settlement cell, or certainly the live end of it, if you like, the monitoring end. This is a single point. This measures settlement at a single location. It's installed at original ground level prior to levels being raised. And the resultant plot on the right here demonstrates the settlement of the plate relative to the datum, and also shows the time series of loading history shown on the secondary axis here, which is important to help interpret the ground movement. We can also monitor movement in a horizontal plane using a hydrostatic profile gauge, where a gradated pressurized pipe or probe is traversed horizontally through an access pipe. And then you can measure settlements at any particular given point repeatedly over a period of time. And again, we have here an example of recorded settlements and the corresponding load surcharge height over the top. Typically 50 to 150 meters of length. Any greater than that, it becomes impractical and fairly unwieldy. It is, yeah, can be quite hard work, but very good data, I think. Right. Okay. Characterizing the settlement behaviour of fill, deep or less deep, or can be achieved by undertaking large-scale load tests. It does require available material. The image on the right, the load test there, is taken from the former Orgreave colliery, now the Waverley development over in Rotherham in 2009. And the volume there is about 6,000 to 7,000 cube. Prior to construction, we installed these settlement pins. These were precise levelled, and a little bit of careful thought needs to be given as to how the mound is constructed without deflecting the measurements of these settlement pins. And it's key, quite a bit of a settlement will occur during construction, and particularly if it takes a while to construct, in which case having a good control of precise levelling of each of these survey pins and close supervision is important. Ooh. Sorry, there we are. Here we can see a constructed load test, slightly smaller in volume and in footprint. But here the load was applied effectively instantaneously, only taking a day to achieve the required height of 5 meters, inducing effectively 100 kilonewton load to the underlying fill. A magnet extensometer was drilled beforehand and extended up during construction of the mound, so we could get a vertical profile of settlement at depth. On a slightly smaller scale, but relevant to house building end use, stacked skips can be used to measure settlement of the founding concrete pad. And here you can see on the outside we've pre-drilled some boreholes to inundate the formation with water to examine the collapse compression settlement mechanism at a later stage. You can install these over the top of magnetic extensometers. It does get a little bit tricky, and a little thought needs to be given as to cutting holes within the bottom of the skips and reinstating those holes when you return them back to the supplier. Central to a lot of data collection is surveying and having confidence that the data is robust and QA'd. Thought needs to be given onto the type of ground marker that's employed, be that a ground grip marker or a phenotype marker with ground anchors, distribution and monitoring frequency of these ground markers, checking that the control is stable, the map itself is not settling or is away from ground that could settle, checking the datums to demonstrate that, and the key one is preservation of the pins, particularly on a live site where they can become damaged, etc. So we're going to move now away from the data collection, and so what next? And that will be with regards to ground movement, the geotechnical modelling aspect. One of the questions to address is how much settlement can we expect? Can the development tolerate this settlement? Can the ground support the proposed end use? And what measures may need to be put in place to allow the end use to be achieved and designed appropriately? Are we looking at some form of ground treatment? So we have an open cast backfill in this cross section here. We've installed our magnetic extensometer. And again, the eagle-eyed of you may wonder why it isn't bedded into rockhead, and that's just due to the offsets of the cross section. So it is actually bedded into rockhead. So we have a magnetic extensometer, which has been recording settlement depth through the profile. And one of the geotechnical modelling questions is, what settlement can we expect from raising of levels by the placement of engineered fill to create a level platform? And what sort of settlement can we expect from a construction load from the placement of, in this case, a commercial unit with pads and a ground bearing floor slab? Based on settlement data and in situ testing during the ground investigation, stiffness profiles can be back calculated based on the observed settlement to derive a back calculated stiffness profile. These stiffness profiles can then be used to model the anticipated short and long-term settlement. Assumptions are made on the foundation type, for example, as I mentioned earlier, pads or ground bearing floor and a ground bearing floor slab, with pad spacing dimensions and slab loadings assumed for initial purposes. This is an iterative process and rerun once building loads are confirmed, and the differentials between the pads is also modelled. So on the assumption that the settlement is beyond what could be tolerated, then we need to think of ground treatment. Bear with me, there we go. There are a range of ground treatment options, notably dynamic compaction, rapid impact compaction, shallower energy type methods using some form of high energy impact compaction, or over digging and replacing materials, or a combination of. For the purposes of this talk, we'll be covering ground treatment by surcharging as one approach, whereby from surcharging we apply a load equivalent or in excess of a construction load and it offers an effective method of ground treatment to induce the required settlement. Depending on the dimensions of a treatment mound, it is possible to stress the ground to great depths, typically the full depth of an open cast backfill, but this does require a sufficient volume of material to do so. Multiple movements of material can be used, which needs careful documentation for production of validation reports, etc. Here we can see the surcharge treatment of underlying backfill material, showing the interface between showing the backfill in grey. This was instrumented prior to surcharging with vibrating wire plate settlement cells and buried monoliths of concrete with for survey pins. Following construction, rapidly drilled and installed borehole magnetic extensometers from the top of the surcharge down to the base of the excavation. And, yeah. Okay, so we'll just move on now. So ground treatment as an approach. So here we have a commercial building outline of where it may well be idealised to go. Ground treatment simplified here with application of a surcharge mound. Crest can extend beyond the building line. Obviously requires a lot of material. If we look at the original landform, this light green section here highlights where levels have been cut to achieve a level platform. And this ground will already have benefited from preloading, be that of varying extents. Over on the left-hand side, it will have benefited from not so much loading, but over on the right, in the red area shown here, for illustration purposes, it could well have benefited from 5 meters of cut, equivalent to 100 kilonewtons of load. So we can start to think, okay, well, actually, we don't need quite as much material as we initially thought. So the cost implications and the time implications for bringing it to development can be shortened and reduced by treating the parts of the building footprint that require treatment. Moving on in terms of ground movement to the last 2 remaining areas, we've got location of mine entries. Ooh, there we go. So mine entries, this is a site involved with in St Helens. We can see the Coal Authority recorded position of a shaft in blue. By checking the primary data sources of information shown here, which were gained from the abandonment plans shown in the yellow, orange and red circles, there's a slight difference of where the shaft could well have been plotted. So we can use the 10-meter departure set by the Coal Authority on this particular instance and plot where we think the shaft may well be. And of course, you know, you start the investigation on a square spiral, or you can you know, take an educated or an informed decision as to where to start drilling. Either way, checking the primary data is a good way to go. And then on the right here, we have an image of a rotary rig undertaking a mine shaft investigation from a platform. Historic caps can be present, and here we've undertaken an exercise of locate drilling across and tapping the top of the cap, dropping off, shown by the so the cap is shown by the blue probe holes, and the brown is the edges of the caps. So with a conjectured dimension, lateral extent of the caps and vertical profile taken from coring, you can see some reinforcement bar on the top of the core here, sorry, within the core. This is all undertaken with agreement with the Coal Authority. We can undertake a structural analysis to see if the cap is suitable for retention for the, in its current state. So structural engineers over at LDE have undertaken this, and in this particular instance it wasn't appropriate, so we had to design some an alternative remedial cap. It was too deep to fully expose, so in this instance we tried to improve the overlying made ground from rockhead, and then excavated down and founded the new cap at depth and reinstated back to development level. This was all undertaken through engineering appraisal with the Coal Authority through their pre-application process to meet the client's needs for development. Moving now on to the third element of ground movement and shallow coal workings. This is whereby voids or broken ground can reduce the bulk density overlying the workings that have collapsed. And so to illustrate this, again from a Charleston site, from Neil's involvement there, we can see the pillars, we can see where the coal's been removed, and we can see the void migration started here, and it started with some collapse. So the shallow coal workings, they can extend in some circumstances, certainly not all, but in some circumstances underneath high wall areas, in which case that would need treating. So here the seam is dipping to the south or the left of the image from the ground model, and drilling and grouting consolidation treatment being undertaken on the left, with the treatment plan on the right-hand side on a primary grid, secondary grid, and reducing to a tertiary grid in locations. It's worth noting that the site boundary here, shown in red line, is constrained to the north. If that wasn't the case, then the light green area is an area of that former old open cast area, in which case, the site could be optimised to move over a full depth of excavation. As it was, the site was constrained by the current plot boundary. Okay, so closing remarks. We briefly covered coal mining legacy in the UK and some of the geotechnical challenges that these pose. We've briefly covered some approaches to assessing ground movement through data collection, modelling, and ground treatment by surcharging. We've also briefly covered the location and treatment of mine entries and shallow coal workings. I think it's also worth just mentioning here, even though this is closing remarks, is to highlight this slide, which we started in the introduction. You can see this is the black and white coal seam, which is removed by UK Coal, and they've broken into an old open cast area on the left of the image. You can clearly see the in situ natural glacial deposits, the weathered rockhead horizon, and you can see the high wall coming down here, which was from the 1950s. And really, it's this area here, and also the rapid changes in lateral movement, lateral distance on the high wall areas, which present a challenge to the consultants and assessment. Let me remove that pen. Yeah, so sorry, wrapping up on the closing remarks, I wanted also to comment that whilst all things below the ground and the effects they have on the scheme are clearly important, the delivery of schemes is a result of collaborative working between clients, consultants, regulators, and the wider design team, and in some cases, the future plot purchaser. Key guidance to be aware of, if not already, is the Syria C758D Abandoned Mine Workings Manual and the Coal Authority Guidance for Developers, shown on the right here. Two important documents, as too is the BRE Building on Fill Geotechnical Aspects, and Galloway's 1882 book on the right is brilliantly written and thoroughly engaging. And if you haven't read it, I couldn't recommend it enough. It's a super book. And thank you for your time. Please feel free to drop me an email if you have any questions. Now switch my camera on and hand back over to Mark.
Thank you, Sean. That was a very interesting, enlightening talk. We'll get stuck here straight into Q&A. We've had a few come in. There's still time for if anybody wants to put a question, we can get them included. So let's kick off with one. So, limiting factor to surcharging as a ground treatment option is the availability of material. So, does this preclude the use of this option for smaller sites?
No, not at all. I take the point that certainly some of the slides shown there have been large volumes of material, but it very much depends on the ground conditions that are present and the depth of fill that requires to be treated, and so it doesn't preclude that at all. There's through careful look at the ground conditions for proposed end use, cut to fill drawings and tweaking and optimizing that to generate materials. It absolutely can be used and has been used on smaller sites.
Okay, we have one here. What are permitting requirements for remediation of coal sites and recovering soil from mine workings?
The permitting requirements in...
This talks more about the geotechnical rather than the environmental side of things, but that's from George Evans. We can get back to you, George, on that.
Yeah.
unless you've got.
I'll have to have a think about on that one, Mark. I mean, I'm not entirely sure what permits is no good.
Oh, that's a different team, it's fair to say. Can you comment on how geophysics can be used for defining open cast high walls?
Yeah, they've the geophysics team have undertaken that for geosciences within the business, and yeah, I believe they've had successfully used that successfully.
I've certainly worked on sites where certainly you have your plan of the high wall, and that was just the last plan, and isn't necessarily where the high wall was found. And we go and do the geophysics and the subsequent drilling and excavation works. So it can be very useful to target your excavation.
And I think the key thing is it's a blend of approaches, isn't it, to validate, to ground truth, and to limit resources to try and find it. Yeah.
Certainly, if we go back to the environmental side of things, people have often asked us whether mine waste material can be used in an MMP, and at the moment the answer is no. So that's something to bear in mind, because it's classed as a mining waste. So I think that's all the questions that we have in for today. So, well, we had over 140 attendees today. So can I thank you all again for attending this Down to Earth webinar. Our next webinar in February is going to be on ground gas and soil vapor risk assessments. So I hope you can join us again. Thank you again and enjoy the rest of your day. Bye-bye.